Hello, today we're going to look at what causes a rainbow. In my recent video on waves, I considered refraction, and I thought it might be interesting to look at how refraction is really the root cause of a rainbow. Now, a rainbow arises when the sun is shining, or indeed if there's any bright light. You are standing on the ground and it's raining somewhere over here. And what you will see in the sky is a rainbow. And what is actually happening is that light from the sun is hitting the rain and being reflected, and somehow, as we shall describe in a moment, giving the effect of a rainbow in the sky. So I've pre-prepared my drawing, otherwise there's a risk I won't get it right and it will be confusing. This is a raindrop. Of course there are millions of them, but this is just one raindrop. And light from the sun is coming in this direction. Now, it looks as though it's coming in, as it were, parallel to the Earth. It could be coming in at any angle. It doesn't matter. The geometry will be the same. You can spin it round like that if you want to. But for these purposes, we'll just keep it like this to illustrate what's happening. As it hits the water, which is the raindrop, it will, of course, be refracted, and it will change direction. Now we're going to draw a normal to the raindrop, and that normal, of course, will by definition go through the centre of the raindrop. And what we know is that this is the angle of incidence, and this is the angle of refraction. Now, when it gets to here, some of the light, not all, but some of the light will be reflected. And once again, we can draw a normal to that surface. And here we shall have an angle, which is strictly the angle of incidence, and this is the angle of reflection. That's my clock again. But I think you'll see that since this is the radius of a circle and this is the radius of a circle, this is an isosceles triangle. And therefore, if that angle is R, that angle must be R. And if that angle is R, that angle is R, because that's the angles of reflection are the same as the angle of incidence. And now, so there's the passage of the light ray. The light ray now comes down here, where some of it will be reflected, but some of it will be refracted out of the raindrop. And once again, we take the normal to the surface of the raindrop. Here we have an angle which, of course, by definition, since this is also the radius of the circle, and this is now an isosceles triangle, this is also R, and this angle here is the angle of incidence backwards, as it were. So effectively the light has gone this way and it's come out that way. And if we draw another beam in parallel, what the light has actually done is it's gone through an angle of phi. And what you can show is that phi is equal to, sorry, not sigma, phi is equal to 4r minus 2i. So, quick reminder of what's happening. The light from the sun comes in. It is refracted because it's going from air to water. It goes over here. Some of it will be refracted out, but we don't care about that. It's what's reflected that matters. It's reflected down here. Some of it will be reflected again. We don't care about that. It's what's refracted out that matters. And the angles are all the same here, R, because these are all isosceles triangles. And so the light has effectively gone in from here, it's come out here. If we draw that line parallel to this line, we see that the change in angle is the angle phi. And phi is equal to 4r minus 2i. And what you can show by applying Snell's law is that phi has a maximum angle, and that is approximately 60 degrees. It cannot get any bigger than that. And that means that light from this raindrop comes out in the form of a cone. Where this angle here, phi, is a maximum of 60 degrees. No light will emerge from the raindrop here, or indeed here. But, and here's the key point, the refractive index varies according to the colour of the light. For red light, the refractive index is 1.331. For violet light, the refractive index is 1.343. And that means that phi max for red is about 59.53 degrees, but phi max for violet is 58.83 degrees. The red has a higher maximum phi than violet. And that gives us a slightly different nuance now. And that is that this cone of light which emerges from the raindrop, remember no light can come out more than that angle, will look like this. That's the red light maximum cone, but within it is a purple light maximum cone. So the outer one is red because it has a bigger angle, and the inner one is violet because it has a lesser angle. And of course the colours in between red and violet will be in between these two parts of the cone. In the middle, all colours come out, and all colours are white. Outside, no colours come out. So effectively, that's just black or dark. Well, what does that mean in terms of my capacity to see a rainbow? Here I am, standing on the earth, looking up at 3 raindrops. Here's raindrop number 1. Of course, there are millions of them. I'm just picking 3 at random just to prove a point. And there is the cone of light. And when I look up at that, I will see no light because the light that comes out, there is no light coming outside that cone. Here, on the other hand, is another cone of light. This time I'm looking right into the middle of the cone, and so I will see white light. But there is a cone such that when I look up at it, I am seeing straight along that line there. I am seeing red light. So if I take this example here, let's just blow that up a little bit. That is the angle for red light. This is the angle for violet light. And I will therefore need to move that cone. If I'm seeing it here, I can't see the violet light, I can only see the red light. But if that raindrop were a little lower, or the cone is going down a little bit more, then the violet light will now reach me. And so consequently I will see the red light higher in the sky than I can see the purple light, from different raindrops of course. So what does that mean? Above the critical angle, no light is reflected from the rain. Well below the critical angle, all light, all colours, which will contribute to white light, are reflected by the rain. At a certain angle, only red light can be seen. At a slightly lower angle, here, you can go through orange, yellow, green, blue, indigo and violet, and that will be a narrow range, and from there on ever after, all you see is white light. And that, of course, will be a pattern across the whole sky, and that's why you see a bow And the bow, of course, is such that red is always on the top, because it's red that you see higher up, and it's violet that you see a little bit lower down. So red's on the top and violet's on the bottom. Now, there's a question that you might be asking yourself, and that is that when you're looking at, let's say, yellow light, then not only are you looking at yellow light, but you're also looking at red light and orange light, because once you've got past the critical angle, that red light will continue to shine all the way down. So initially, the only light you see is red light. Then, as the raindrops are a little bit lower, you get red and orange, a little lower, red, orange and yellow, a little lower, red, orange, yellow and green, and so on. And you might wonder, therefore, why you can still see these colours distinctly in the raindrop, if in a rainbow, if as you go down in this angle, you are seeing more and more colours. Why don't they just all merge? And the answer is that it's to do with the intensity of the radiation, that in practice, even though by the time you're looking at the violet line, you are in fact seeing all the colours, because of course, as soon as you get past the violet line, inside this rainbow will be white light. Nonetheless, the violet is sufficiently strong that it gives you the intensity to your eye that you can still pick it out. And here's a picture I took in my own back garden of a rainbow. And you'll notice three things about it. Firstly, that the red is at the top and the violet is at the bottom. And secondly, you should notice that above the rainbow it's very dark, but underneath the rainbow, within the bow itself, it's significantly more light. And I hope now you understand why that should be. Now, the position of a rainbow in the sky is going to depend on where the sun is. If the sun is low in the sky, the position will be high, the rainbow will be high in the sky. If the sun is high in the sky, the position of the rainbow will be low in the sky. Sometimes you'll see the effect of a double rainbow. There is often another rainbow above the main rainbow. And in that case, red is at the bottom and violet is at the top. In other words, it's the other way round. And the reason for this, we won't do the detail of the mathematics. The reason for this is that you can have a situation where the rain actually has three reflections in the rainbow, in the drop of rain, and the light goes in, it's reflected three times, and it comes out this way, and that will give you a rainbow higher in the sky and inverse, whoops, let's get it down here, higher in the sky and inverse in terms of its colours. So the main rainbow will have red at the top, violet at the bottom. The secondary bow, if you can see it, will be violet at the top and red at the bottom. And that's because there's one extra reflection in the raindrop that gives that effect. I hope that explains how a rainbow is formed. Hello, today we're going to look at what causes a rainbow. In my recent video on waves, I considered refraction, and I thought it might be interesting to look at how refraction is really the root cause of a rainbow. Now, a rainbow is a raindrop. Of course, there are millions of them, but this is just one raindrop. And light from the sun is coming in this direction. Now, it looks as though it's coming in, as it were, parallel to the Earth. It could be coming in at any angle. It doesn't matter. The geometry. Rainbow arises when the sun is shining, or indeed if there's any bright light. You are standing on the ground and it's raining somewhere over here. And what you will see in the sky is a rainbow. And what is actually happening is that light from the sun is hitting the rain and being reflected, and somehow, as we shall describe in a moment, giving the effect of a rainbow in the sky. So I've pre-prepared my drawing, otherwise there's a risk I won't get it right and it will be confusing. This will be the same. You can spin it round like that if you want to, but for these purposes we'll just keep it like this to illustrate what's happening. As it hits the water, which is the raindrop, it will of course be